Good joke, Evan. I like that. All right, let's start a new topic. Okay, enzymes. My second favorite topic. What is my first favorite topic? A lot of different topics, actually. Chromatography is one, protein is another. But this is also a great topic, a lot of applications. We use enzymes in food analysis. Enzymes are everywhere in the food in general. So do you know what keeps the syrup in the chocolate-coated cherry like this, not crystallized? You know, sucrose can crystallize over time. And if you don't want that to happen, what do? You don't know? You have not covered that in food chem? Okay, so you actually hydrolyze sucrose to break it into fructose and glucose, which do not crystallize as fast as sucrose. So during storage, you maintain that syrupy, non-crystallized texture. In corn, why do we care about corn? What do we produce from corn? What's a common ingredient? High fructose corn syrup, and this is all based on enzyme utilization, production of breaking down starch into glucose by enzymes and then converting glucose to fructose. So what's the relevance of enzymes in your orange juice? Do you want your orange juice to be cloudy, or do you want it to lose the cloud? If you have juice with pulp, do you want the pulp to separate, sediment, or you want the juice to be cloudy? The orange juice specifically, not apple juice. You don't want a cloudy apple juice. But you really want to maintain a cloud in orange juice, so you basically need to make sure that methyl esterase is being inactivated. And then you measure that later on. So methyl esterase, you would remove the ester and you will have more negative groups. Then what happens is that the calcium will form bridge between the different pectin molecules and make it precipitate. So you will end up having a separated orange juice, which is not something you want. Another example here is your flour. One particular enzyme that is commonly measured, or the activity of it is measured, is alpha amylase. But because if you have highly active alpha amylase, what happens is it will break down your starch in an application, then you reduce the viscosity of the starch in your application. So it's directly related to the quality of the flour in terms of starch quality. So these enzymes are relevant, they're important, we analyze them, we look for them. Okay, so if in food systems in general, can you name an example where measuring of the enzyme or use of enzyme or the presence of enzyme is relevant?
So you reduce the activation energy of your whatever reaction that you do.
Yeah, what would be a category of application? Yes, exactly. We want to inactivate unnecessary enzymes to enhance shelf life. So blanching, for example, a process that will inactivate enzyme, how is that relevant to analysis? Because you measure peroxidase activity after blanching, or lipoxygenase activity, because they are the most heat-stable enzymes. If these are inactivated, that means that all the other enzymes are inactivated as well, and you have better shelf life. Good. So that is related to quality, Zach.
Breakdown of large molecules into smaller molecules, or vice versa, smaller.
Yeah, well, breakdown. That is an application when we talked about measuring starch content, for example. We had to break it into glucose. And then we used enzymes to measure glucose. So we use enzyme as preparatory step, and we use enzyme for quantification of certain constituents. For fiber, last Wednesday, we talked about fiber determination, preparatory steps. We had to use enzymes, break down the starch, break down the protein. So we use enzymes as preparatory step, and we use enzyme to quantitate constituents. Good, what else? Yes, Ted. Yes, polyphenol oxidase. We need to inactivate polyphenol oxidase or prevent it from being that active. For example, they kind of engineer apples, certain, I think Granny Smith apple probably is engineered so it has low PPO activity, so it won't brown as fast when you cut it and sits for a while until you eat it. Let's see what else we have. We talked about sample preparation, an example of quality, another example of not necessarily quality, but determining whether a process was efficient. We talked about blanching, but another important application to determine efficiency of a process is in pasteurization of milk. So instead of determining the presence of pathogens after pasteurization, or making sure that all the pathogens have been killed, because it takes a while to measure pathogens. Micro takes a while. So you can measure the alkaline phosphatase enzyme. So alkaline phosphatase is more thermally stable than the pathogens. So if it's inactivated, then you know that your milk has been properly pasteurized. So it's one of the quality assessment methods that you would do on an incoming pasteurized milk to ensure that it was pasteurized before utilizing it in a product. Measuring activity, sometimes you want to make sure trypsin inhibitor has been inhibited in a soy product, because high amount of trypsin inhibitor will interfere with our digestion system, because we have trypsin that digests proteins. So you measure the inhibition of trypsin inhibitor by using trypsin in an assay and determine whether or not that trypsin was inhibited by an extract from soy. Let's see, processing tool, we gave the example of using enzymes to produce high fructose corn syrup, for example. Waste management, so sometimes waste stream have proteins residue, lipid residue. So instead of having those streams going through the drain as is and clogging the drain, sometimes you have a treatment with enzyme to break them down and make them more soluble so they don't block the drains. So a lot of applications of enzymes, basically. Quite a bit. Because of that, we isolate enzymes and we characterize the enzyme kinetics in order to understand the enzyme activity. If we want to inhibit it, we want to make sure what are the conditions that would make the enzyme active versus conditions that would make it inactive. So we really need to study the enzyme kinetics. So understand the velocity, maximum velocity, understand the affinity, understand inhibitors. How do they all come together in order to design enzymatic reactions, to quantitate, or design a procedure to inhibit enzymes? So we really need to understand the kinetic in order to be able to utilize them or inhibit them. Okay, so I'm sure you touched a little bit on that during food chemistry, so I'll give an overview that is relevant to analysis, and hopefully what you learn in food chemistry and analysis makes the picture a little complete, and chemical reactions come back to enforce certain topics. Okay, so from the very beginning, just a small refresher about how the enzyme works. Enzyme reduce what Nico said earlier, reduce the energy needed for the reaction to go forward. So reduces the activation energy, basically. and speeds up the reaction. So it is a biological catalyst compared to a chemical catalyst, for example. So, and there are different reaction rates, 3 reaction rates that are of relevance. E plus S to form the ES complex. So here you have the substrate and the enzyme. To get a substrate enzyme complex, your reaction rate is K1. You get ES. And then from there, after ES, the reaction moves forward, the enzyme is released, and products are formed. Okay? So this would be the reaction rate for the second path. But also ES can go backwards. So it is not a permanent reaction, and not a, it's a dissociated, they can associate and dissociate is what I want to say. So they can form a complex and then they can go back to individual components. So ES can go backwards here or can go forward. If we saturate the reaction with substrate, your reaction will be driven that way for the production of product. If you have enough substrate in the system, the reaction will be driven mostly forward. Okay. So usually when you're using enzyme and you're running an enzyme reaction, so there are 2 important components that you keep track of: time of the reaction and the product. Because oftentimes the product is what gets measured. Sometimes you measure substrate absorbance, but oftentimes you are measuring the product or the absorbance of the product. So when you're looking at kinetics of the reaction, so you would measure it at a particular substrate. So you would monitor the time, and then you monitor the product, and then you plot this curve. So what you see is that the curve starts very low slope, and here nothing is happening much other than the E and S are binding. So this is the pre-steady state. Once they are bound, then we get into the steady state where the rate of disappearance of ES equal the rate of appearance. That means this is the rate of appearance, E plus S, you get ES. Rate of disappearance is both K2 and K negative 1. So it's going this way and going that way. When we have equal rate, then we call this steady state, and that's where you can measure the velocity of the reaction. You take the slope and you get the initial velocity of your reaction. In kinetics, you really need that initial velocity. It's very important to get that. And where you get that is here in the linear portion, where you're monitoring absorbance of that product over time. So you're monitoring absorbance and calculating the concentration at different time points, then you can get that curve. What do you think is happening here? Why are we getting plateau over here? So with more time, we're no longer getting much of a product change. What do you think is happening over time? So what is converting to a product? Yes, Megan? Yes, thank you. So you have substrate and you're getting product. Over time, you're running out of substrate. So you lose the linearity and it plateaus when you are depleting your substrate. Good, so let's review a few terms. So the initial velocity is the slope during the steady state before the product starts to, the formation of the product starts to become, to level off, that is. And then maximum velocity, here's where maximum velocity comes into play. Maximum velocity is the maximum rate of the reaction that can be obtained, okay? So it is a function of the substrate. So basically, if we run the same reaction at different substrate concentration, So this is at one substrate concentration, and then we run it multiple times, and I got the initial velocities at each concentration. Then I can plot that. I can plot the initial velocity at every concentration. Initial velocity of the enzyme at every concentration. When I plot that, I can see the impact of substrate concentration on the velocity of the reaction. Vmax here, you can see that at high concentrations, we reach Vmax. That means, very simple, when your enzyme is saturated with the substrate, when we have an abundance of substrate, your enzyme is functioning at the highest speed. Okay. Another important term that you'll come across is the Michaelis constant or the Michaelis-Menten constant. So the Michaelis constant is basically an amount of substrate or concentration of substrate, but at a particular point in the reaction. The Km is the substrate concentration at half Vmax. So if I ever ask you to define Michaelis-Menten, you have to say two things. You have to know that it's the concentration of your substrate when Vmax, when velocity is at half Vmax. And the next thing you want to say, it is a determinant of the affinity of the enzyme to the substrate. Why do you think it determines the affinity of the enzyme to the substrate? You remember that from your food chem? Or any, I'm sure you've taken enzymes somewhere else. Do you know why it indicates the relative binding affinity of the enzyme for a specific substrate? Let me give you a couple of assumptions here. So Km for substrate 1 is greater than Km for substrate 2. So looking at the figure there, and we have enzyme X, have Km to substrate 1 greater than Km to substrate 2. This enzyme would have higher affinity to substrate 1 or higher affinity to substrate 2. Take a moment, think about it. Axel?
Has a greater maximum velocity.
But which of these substrate the enzyme has more affinity to? Substrate? I got excited for a second. No, substrate 2. The smaller the Km, the higher the affinity. Because look at that. So this. So if I have higher Km, then I reach Vmax somewhere over here. So when you reach Vmax at lower substrate concentration, that means you have the enzyme is latching on to the substrate really quickly. It has high affinity to it, so you're reaching Vmax or half Vmax at a smaller concentration. So this means the enzyme has more affinity to it. When we reach Vmax or half Vmax at higher concentration, that means I need more of that substrate to reach half Vmax. That means I don't have that much of affinity to that substrate. Okay. So Km and Vmax are affected by different characteristics. Some of them are really similar, but the nature of the enzyme and the nature of the substrate obviously impact affinity. And it's also impacted by pH, because you have optimum pH for enzymes, optimum temperature for enzymes, and presence of inhibitor will also impact how well the enzyme can latch onto the substrate, or the substrate latch onto the enzyme. Vmax is also impacted by enzyme concentration, substrate concentration, of course the pH and temperature, and also presence of inhibitors. Here's something you need to remember, which is very relevant to analysis, food analysis. This is really an important slide. for food analysis specifically. If I ask you in the quiz, if we want to measure a constituent, if I want to measure glucose, okay, I want to make sure that my reaction rate is first order to the substrate concentration. I don't want to work in saturated zones. Then it will be zero order to substrate. I want to make sure that the order of the reaction is first order with respect to substrate. That means it's impacted by a change in substrate concentration. Because it's impacted by a change in substrate concentration, I can quantitate that substrate. Okay. On the other hand, if I want to measure enzyme activity, I want to make sure that I have enough substrate, and the substrate is not the limiting factor in my reaction. So in this case, I want to make sure that I have much high concentration of substrate, much greater than Km, so I reach Vmax. Then the velocity will be impacted by the concentration of the enzyme rather than the concentration of the substrate. Because I'm measuring peroxidase, I'm measuring PPO, I'm measuring what rennet enzyme activity. In this case, I want to make sure I have an abundance of enzyme, so the change in the reaction or the change in the product I'm seeing would be directly related to a change in enzyme concentration, not substrate concentration. So that's why I want it to be zero order to substrate, not impacted by substrate concentration, but really impacted by the concentration of the enzyme. So if I want to determine Km and Vmax, which are important terms to understand the kinetic of the enzyme, so I can set up an enzymatic reaction. In order to set up an enzymatic reaction, I need to know how much substrate to use, how is the velocity of the reaction is going to be impacted. So I really need to determine the Km and Vmax for every enzymatic reaction, for every enzyme and substrate combination, so that I can set up my enzymatic reaction. So to do that, I need to figure out a way to calculate Km and Vmax for every situation, for every enzyme substrate combination with and without presence of inhibitors. I need to figure that out. So how to figure that out? I need to get some parameters to help me figure that out. So one thing I want to do, the main thing I want to do, is I want to run my enzymatic reaction at different substrate concentration. That is very important. I really need to prepare solutions at different substrate concentration, mix them with the enzyme, and monitor the reaction rate at every concentration. And then plot the reaction rate over substrate concentration, and then I get sort of an equation of a nonlinear line. We know that linear is always better than nonlinear in calculations. So, Lineweaver-Burke plot. So these two scientists came up with, okay, let's convert this to a linear plot. So all they did is they plotted the inverse, 1 over velocity, 1 over substrate concentration. And they came up with an equation of the line. So this equation became this equation. So here, 1 over V0 is your Y, 1 over concentration of substrate is your X. Yes?
So as the reaction goes, you're basically starting somewhere like on the right and moving left on substrate concentration, right?
Starting here.
Starting on the right at a higher concentration, and then as it progresses, you're moving left.
No. You are preparing individual reactions separately. So you're preparing a mixture at concentration, let's say, of 1 millimolar, and putting the enzyme and monitoring the velocity. And then you prepare another reaction with a different concentration and monitor the velocity.
The individual ones would have tendencies to kind of follow that line as they progress.
No, no, the individual ones will follow this. The individual is what you're monitoring. You're monitoring product over time for every concentration. You're monitoring product over time and you get a slope at the steady state. That's your initial velocity. So you get an initial velocity for every reaction and you plot that at the concentration. Good question though. It's good that you want to understand that piece. All right, so, which is right here. So this is what you get. So you monitor product over time, get the velocity, plot inverse velocity over inverse concentration. Okay, so you get the equation of the line, which is y equal km over v max, that's your slope. 1 over concentration of the substrate is your x. And then 1 over v max is your intercept right here. So you get the equation of the line, and then you can calculate v max because it's your intercept. And then since you have v max, you have the slope, you can calculate km. So now you know the km, you know the v max for the combination of X enzyme to Y substrate. Then you can develop a reaction using that enzyme to that substrate. All right, this is a good stopping point. Next week we'll talk about factors that affect enzyme reaction rate. Okay, have a great weekend.